Okay, so the recording started. Okay, so this is the problem, and we are finding the expected value of each possible value, each possible y sub I. Okay, so to illustrate this problem better, I'm going to put on the whiteboard a table. Okay, so this is our PDF function, and I'm going to put a table here. Okay, let me go to the whiteboard. So okay, here's little x. Okay, so here's capital X. So capital X could be 3. It could be 4. It could be 5, and it could be 6. Right? The number of requests for a magazine could be 3, 4, 5, or 6. Y sub 3, right, tells you how many magazines he got in advance. So if he buys 3 magazines, Y sub 3 are the profit he makes, assuming that he buys 3 magazines. Y sub 4 is the profit he makes, assuming he buys 5 magazines. Y sub 5 is the profit, assuming he buys 5 magazines, and Y sub 6 is the profit he makes, assuming he buys 6 magazines to sell. Okay, and then the X, remember the X is the number of requests for magazine. So it's the number of requests. So X is the number of requests for magazines, and the Y's are the amount of profit, assuming that he buys that many magazines in advance. Okay, so it's $1 it's $1 to sell a magazine, right? He makes $1 to sell a magazine, plus 1 to sell a magazine, but it's minus half $1. It's minus 50 cents, right? Or $0.5. It's minus $0.5 to get a mag to sell. Okay. Because you have to keep these things in mind, and we have a PDF function that I defined for you on the whiteboard on Word, right? And f of x, which f of x whose possible values are we have 5/12, we have 4/12, 2/12, and 1/12, right? And so this is when x is 3, x is 4, x is 5, and x is 6. Okay, so each of those values actually have those probabilities. Okay, so that's all the information essentially that was on Word. So so this is $1.50. If he bought 3 magazines in advance, he paid $1.50 for those 3 magazines, but he sells 3 of them because he has 3 requests, so he makes $3. So if he loses $1.50 and makes $3, the net gain is a plus $1.50. Okay, still assuming that he bought 3 magazines in advance, values of Y sub 3. If he has 4 requests, he can't meet the 4th request. So he only sells 3 magazines, the 3 that he got. So it costs him $1.50. He makes $3. The net is $1.50. So even though there's more requests, he can only fulfill the first 3 requests, and all the additional requests, he just can't make more money. And so he makes a total of $1.50 in each of those cases, assuming that he bought 3 magazines in advance. Now, these are all possible values of Y sub 4. He buys 4 magazines in advance. Each costs 50 cents. So 50 cents times 4 is $2. So it costs him $2 in advance for these 4 magazines he wants to sell. So there's a minus 2 of anything here. If he sells 3 magazines, he makes $3. So if he makes $3 after spending $2, he gains a net total of $1. And so if only 3 people request magazines, he only makes $1 because one of the magazines he bought in advance was not sold. Now, if 4 magazines are requested, well, then he can sell all 4 of the magazines he got. And so it costs him $2, he makes $4, and he makes a total net of $2. Okay, now if there's 5 requests for magazines, he can only satisfy the first 4, and then the 5th person just can't buy a magazine, but he still makes $2 because he sells all 4 magazines that he has. So he makes $2 in all the other 3. cases. For y sub 5, he gets 5 magazines in advance. Each costs 50 cents. 50 cents times 5 is $2.50. So he spent $2.50. If he then sells 3 of them, because he has 3 requests, $3 minus 2.5 is then 50 cents. And so he makes a net of 50 cents if there are 3 requests. If there are 4 requests, he makes $4. And he spent $2.50. That's a net $1.50. So he makes $1.50 if there are 4 requests. If there are 5 requests, then he sells all 5 because he had 5 magazines in advance. He makes $5. He spent $2.50, and so that's a net total of $2.50. So he makes $2.50 if 5 people request magazines. If 6 people request magazines, he can only sell the 5 that he bought in advance, and the 6th person leaves without a magazine. He just doesn't make more money, but he does sell all the magazines that he got in advance. For y sub 6, he gets 6 magazines in advance. Each are 50 cents, so 6 times 50 cents is $3. So he spends $3 on these 6 magazines to sell. If he only gets 3 requests, he can only make $3 from the 3 that he sells. And so if it costs $3 for him to get the magazines and he makes $3 in the ones he sells, he makes a net of $0. If he gets 4 requests, then it costs him $3, but he makes 4, so he makes a net of $1. If there are 5 requests, then he makes $5 after spending 3, and he gains a net of $2. And then this is the best case scenario, which is usually wouldn't happen. But if he bought 6 magazines in advance, it would cost him $3. And if he sold all 6, then he would make $6, and so that would give him a gain of $3. Okay. And so in this scenario, there is no way he'd lose money. You see, in every possibility, the worst case scenario is that he breaks even. Okay. But in y sub 6, you get the best case scenario that he makes a total of $3. Okay, so these are all the possible values of each random variable. And so to find the expected value of each, you would just take all the possible values and then multiply them by the probabilities. Okay, so let's start with y sub 3. Okay, so let's start with y sub 3 here. What's different about this, it might be a little confusing, is that what are the possible values of y sub 3? There's only one, it's $1.50. Okay, so even though we have 4 boxes in this table, right, they each have the value of $1.50. So the only possible value of y sub 3 is $1.50, and the probability of that happening is 1, right? Because the probability of actually being 3, 4, 5, 4, 6 is 1. You just add up the probabilities in the PDF there. 5 twelfths plus 4 twelfths plus 2 twelfths plus 1 twelfth is 12 twelfths is 1. So the expected value of y sub 3 is the easiest to compute as long as you understand what's happening in the problem. It's 1.5 times the probability of 1.5, which is 1, which is 1.5. So the expected value of y sub 3 is $1.5. Okay, right? Because see how each of these is 150, and the probability of each of these. So you could get this 150 when the probability of that 150 is this. The probability of the first 150 is that. The probability of the other 150 is this, and the probability of the other 150 is that, right? So the only value of y sub 3 is 150, and the probability would be adding those probabilities I circled, right? 1 for each of those values in the table. So it's 1.5 times 1, which is 1.5. Okay, so that's the expected value of y sub 4. Now the expected value of that's the expected value of y sub 3. The expected value of y sub 4, there are 2 possible values of y sub 4, right? There's the value when y sub 4 is, there's the value when y sub 4 is 1, and there's the value of y sub 4 when y is 2. So I'm using green here for this. So the dark green is for 2 and the light green is for $1. So those are the 2 possible values. So the expected value of y sub 4 is 1 times the probability of $1. Well, the probability of $1 is the probability that x is 3, right? So the probability x is 3 is 5 twelfths. So this is 1 times 5 twelfths. Plus, the other possible value of y sub 4 is 2. and it's plus 2 times, well, what is the probability of y sub 4 being 2? It's, well, you have x equals 4, x equals 5, and x equals 6. And so you would add these three probabilities, the three probabilities corresponding to y sub 4 being 2. So that's 4/12 plus 2/12 plus 1/12. That's 7/12. So the probability of y sub 4 being $2 is 7/12. And so you add up those two products, you get 5/12 plus 14/12, and that's 19/12. And so then that would give you 1.58. So the expected value of y sub 4 is 1.58. And so you calculate the other ones similarly. So the expected value of y sub 5 would be, you have three possible values of y sub 5, right? I'm going to erase these circles so that I can focus on the next one. If you're watching this after, when you go to the video, you can then separate the point of the talk when I'm doing one thing and the other thing. Okay, so I'm also going to erase these circles. So I want to use all the, running out of colors. Okay, so so for y sub 5, these are the possible values. You have 50 cents as one possible value. You have $1.50 as another possible value. And then you have a third possible value, which is $2.50, right? So these are the three possible values of y sub 5. And so you take each of those possible values and multiply them by their probabilities. So you have 0.5, which is the first one, times its probability. It's just the probability x equals 3, which is 5/12. Plus, well, another possible value is 1.5. And so what is the probability that y sub 5 is 1.5? It's probably x equals 4, which is 4/12. You can see that from the PDF above. That's 4/12. And then plus, stretch out this. Okay, good. And then plus, the other possible value is 2.5. And it's 2.5 when x is 5 or 6. So you add the probability x equals 5 and the probability x equals 6. 2/12 plus 1/12, which is 3/12. And so when you add these products, you get the value of 1.33. Okay, so that's that one. Now, another, for y sub 6, what are the possible values? The possible values are 0, 1, 2, and 3. So there are four possible values. So the expected value of y sub 6, I guess I can put down here. Just ignore the vertical line. So that's equal sign. Does not equal. It equals. So 0 is one value, but the probability of 0 doesn't matter. But okay, but it's when x is 3, which is 5/12. So 0 times 5/12, which is 0. Plus 1 times 4/12. Plus 2 times the probability that x is 5, which is 2/12. Plus another value, possible value is 3, and the probability that that's probably x equals, probably y sub, another possible value of y sub 6 is 3, and the probability is when x is 6, probably x equals 6 is 1/12. So you have that. So you add up those products, and so when you add up those products as a decimal, you get 0.92. Okay, so the E of y sub 6 is 0.92. And so we now have the expected value of each of those variables. So the question is, how many magazines should he sell to maximize expected profit? He wants to maximize the amount he would make. Okay, so you can go back to the video to have these colors in. I want to get rid of the colors so that we can focus on the expected values of the expected value. Okay, so possible values of the expected value are, so you have 1.5, you have 1.58, you have 1.33, and you have 0.92. So buying 6 magazine exams is actually the worst case scenario. The best case scenario is y sub 4. Y sub 4 has the largest expected value, and so that would be the case of maximizing the amount of profit you would make in the long run, the expected profit. Okay, so the amount you would want is 4. You would want to buy 4 magazines in advance to sell. That would give you the best expected profit. Okay, so so on the whiteboard, we get the answer, which is y sub 4, which is he should buy 4 mags in advance to maximize expected profit. Okay, but yeah, so I saved the whiteboard at the end of class. I can't save it during it because I have to save what the result is. Okay, so somebody else is not joined. Okay, good. Okay, so okay, so the second exam is going to be December 9th. Okay, that's the last day of classes. Okay, so the second exam is on December 9th. Okay. Okay, so major announcement. Okay, so the second exam is on December 9th. Okay, so the second exam is on December 9th, and it covers all the material that is on the syllabus, right? So the syllabus tells you what is on the exam. This is on everything after the cutoff for the last exam. Okay. Okay, so that answers your question, what when the exam is. Okay, so you're good with that. Okay, so there's also a final. The final will be after that day. Okay, the department. So we'll figure that out. Okay, so okay, so next section 6.2.3, which is on the Monte Carlo method. On Monte Carlo methods. Give me 1 second. The exam is going to be the 9th. Yeah. Okay. So good. So that's the last day of class. I just wanted to confirm it. Okay. So I already confirmed it before. I want to confirm it again. Okay. So okay. So December 9th. Good. Okay. That's the second exam. Finals after that. Okay. So example 6.11, Monte Carlo method for evaluating definite integrals. Okay, so let's talk about that. So let's say that phi of u is continuous on a less or equal to u less or equal to b, and is bounded below and above phi So 0 is less or equal to phi of u, which is less or equal to capital M. Consider the experiment, capital S, where a random point u comma v is selected from a less or equal to u less or equal to b, 0 less or equal to v less or equal to capital M. Let capital X be the random variable defined as, so X is going to equal X is going to equal 1 if the point is below the curve of phi of u, and it's going to be 0 otherwise. Okay, so so let me illustrate this situation for you. Okay, but first, what we want is it's called the Monte Carlo method for evaluating definite integrals. The goal is to evaluate a definite integral. Okay, so let's say 5u is continuous on an interval from a to b and is bounded below and above by this. So it's bounded below by 0, bounded above by capital M, this function phi, on this interval. We have an experiment S where we take a random point from this rectangle. This is the rectangle where the first coordinate u is between a and b, and the second coordinate b is between 0 and m. So it's in this rectangle where the length is going from a to b and the height is going from 0 to capital M. So you choose a random point there. X is a random variable defined as, well, for each point in the rectangle, X at that point is 1 if it's below the curve of 5u and it's 0 otherwise. Okay, so your experiment is just randomly selecting points in this rectangle. And if it's below the curve, you get a value of 1. And if it's not, you get, it registers a value of 0. So, okay, so if you have your u-axis and your v-axis, because it's first and second coordinates are u and v respectively, then you could look at u being a from a to b, and the value of the function is between 0 and capital M. And so we're living in this rectangle here. Okay, so we're living in this rectangle right there that I drew between the top 3 sides are dotted, the bottom one is the u-axis. And so if you have a function, continuous function, let's call it phi, that looks like that, where this is phi of u, this is the continuous function phi of u on the interval from a to b, right? Then the our random variable is registering a 1 whenever the random point selected in the rectangle is in that blue region below the curve, and it's registering a 0 when it's not below the curve, when it's somewhere in that region, right? So these values register a 0 for X, and these values register a 1 for X. Okay, and so the goal is to evaluate a definite integral. So notice that the probability that X is equal to 1, the probability that you choose a random point and the value of X, that random point, is 1. The probability of that is the area under phi of u, area under the curve phi of u, which I'm going to abbreviate area under phi of u, which divided by the area of the rectangle, right? So the area of the rectangle, I'm going to draw a rectangle there. Okay, so the probability X equals 1 is the area is the ratio of the area under phi of u, the area of the blue region, divided by the area of the entire rectangle, right? That ratio is the probability X equals 1. It's the fraction of the entire rectangle that the blue region makes up. That's the probability X equals 1. And so now what are the values of the numerator and denominator? The numerator is the area under phi of u. In calculus, you can calculate that blue region as a definite integral from a to b of phi of u du, right? So that definite integral tells you the area of the blue region, and that's the numerator. Then the denominator would be area of the rectangle, but the area of the rectangle is just length times width. And so this side has length b minus a, and the other side has length capital M minus 0, which is capital M. So the area of the rectangle is capital M times b minus a. And so the probability that x equals 1 is the depth integral in the numerator divided by capital M times b minus a. Right? And the probability that x equals 0 is just is 1 minus the probability of the complement event, 1 minus the probability x equals 1. The only two possible values of x, how we defined it, is 0 and 1. So the complement of the event x equals 0 is the event x equals 1 for this experiment. And so if we want to find the expected value of x, then we would just take each possible value of x, multiply it by their probabilities, and then add the products. So E of x is the sum of products, where you take the probabilities. So the probability x equals 1. 1 times the probability x equals 1 plus 0 times the probability x equals 0. But when you multiply 0 times with that probability, you're going to get 0. And so this term goes away. This term becomes 0. That's the only way to worry about 1 times probability x equals 1. So this equals the probability x equals 1. And what is the probability x equals 1? It's the thing we found down there. We found the probability x equals 1 is the depth integral divided by capital M times b minus a. So the expected value is the depth integral from a to b of phi of u du divided by capital M times b minus a. And then that's good. So E of x is equal to that depth integral divided by capital M times b minus a. Okay, and then we can, if you think of this depth integral as a single mathematical object, as if it was like a variable in an equation, we can solve for it, and we can solve for that depth integral, and that we can find that the depth integral from a to b of 5u du is equal to E of x times capital M times b minus a. So I'm going to write capital M times b minus a times E of x. Okay, so the depth integral there is equal to capital M times b minus a times E of x. That's just taking the equal sign. E of x is equal to that fraction. The denominator of the fraction times E of x is equal to that. So we've now found an equation for the depth integral here. We now have an equation. We now have a way of calculating that depth integral. Capital M times b minus a times E of x. Okay, so I'm going to go back to the whiteboard and talk about that equation a little bit. Okay, so we found on the whiteboard that that E of x, that the depth integral from a to b of phi of u du is equal to capital M times b minus a times the expected value of x. So if we perform the experiment of choosing a point at random in that rectangle, if we perform the experiment capital S n times, and little n is large, and letting x sub I and letting x sub I be the value of x on the ith performance of the experiment S, then by the strong law of large numbers, we get that the sum of all those values of x from I equals 1 to n of x sub I divided by n is approximately equal to E of x. with great probability. Okay, so what the circle of the large number says is that the limit of this value is equal to e of x, right? That the limit as n approaches infinity of that fraction equals e of x. So if the limit of this fraction equals e of x, if these, as n gets really large, these fractions are tending towards e of x, to give a rough idea of limit, then if we take n sufficiently large, if we take really large values of n that are sufficiently large, then this fraction should be very close in value to e of x. And so values of these fractions for a little n large are good approximations of the expected value of x, okay? And with great probability. So it's saying that it says that the limit of this fraction is equal to e of x, almost certain, okay? So so if you take little n really large with really good probability, you would get that this is approximately the expected value of x. Okay, and so with that result, we can plug in that approximation for e of x into this equation here, and we can have an approximation now of the definite integral. Okay, so using that, we substitute. So I'm going to call this star. Okay, so we substitute star into the above equation for the definite integral, the one just above the top of the screen, and get that this definite integral, which is equal to this quantity, right? Well, this is approximately equal to capital M times b minus a times, well, now we're approximating e of x as the sum of possible values of x from I equals 1 to n over n. So now we're approximating e of x. We're approximating this guy. We're approximating this guy with this. And so that's why we now have this approximation symbol here, right? So now we have approximately equal, and that is because the two blue things are approximately the same. And this is with great probability. Meaning with probability very close to 1. Okay, so this is an approximation of the definite integral. This is called the Monte Carlo estimate method. So in example 6.12, we are applying the Monte Carlo method to estimate. So this is a Monte Carlo estimate of this definite integral. So the definite integral from 0 to 1 of e raised to the negative u squared over 2 du. Okay, so we want a Monte Carlo estimate of that definite integral. Okay, so let's let phi of u equal to this function here in the integrand of this integral, this e to the negative u squared over 2. And then let's let capital M equal to 1. And so, well, we're choosing capital M equals 1 because this thing is upper bounded by 1. The value of this thing from 0 to 1, because the intervals from 0 to 1, right? So little a is going to equal 0, and little b is equal to 1. This corresponds with the limits of integration of that definite integral 0 and 1, right? Little a is 0, little b is 1. But on that interval, we have this function e to the negative u squared over 2. U squared is non-negative. That can't be negative. And so this fraction u squared over 2 is either 0 or positive. If we're taking the negative of that. So if you take e to the negative something, where that something is non-negative, then it's a decreasing function, which means that its largest value is when the input is as small as possible. In order to make u squared as small as possible, we would want u to be 0. So on the interval between 0 and 1, the largest value of e to negative u squared over 2 would be when u is 0. That's the largest value of it on that interval. And when you plug in u as 0, you get e to negative 0 squared over 2, e to negative 0, which is 1. So I just said quickly is that an upper bound for this function is 1. Its largest value, in fact, is attained, it's 1. And so capital M is 1 is the best upper bound of this function on the interval from 0 to 1. Any other upper bound would be larger. We want to minimize our upper bound. We want to minimize our region that we're using. So capital M is 1 is that. Okay. So now let's approximate the definite. Let's approximate definite integral. Okay. So this definite integral, right, is equal to capital M times b minus a times e of x. And because of the strong law of large numbers, this is approximately capital M times b minus a times the sum over all possible values of x divided by n for large n, right? So it's approximately that. Okay, and I'm putting equals here only because this is now saying that this quantity is going to be equal to the next one. It's still an approximation of the original quantity. Capital M here is 1, and b minus a is 1 minus 0. And we have times that sum over n. So that's 1 times that sum, and so it's equal to that sum. And so now I'm saying that this definite integral is approximately the value of this fraction. And it's for large n, okay? So this is for large n with a great probability. Okay, so this approximation is good with great probability for large n, okay? So there's a random number table in the book, which I'm not going to ask you to use, but using the random numbers in the book, it's table 4, okay? In appendix C, okay? It's part of the book. This is part of the book. What it does is it tells you, it's a table that gives you data on if this would happen. So if somebody chose points at random, it generates results of that random choice of points, right? So if you were to do this experiment where n is 17, okay? So using the random numbers in table 4 in appendix C and letting n equal to 17, we get, so what we get is that when an experimenter chose 17 points at random in this rectangle, what it said, what it said is that the value is 15. Okay, so what we have here is that this definite integral, right, is approximately equal to this. And so what that table is saying is that if you perform this experiment 17 times, okay, that the sum you would get, so you have this sum here, and so you're applying this situation when n is 17. So you're choosing 17 points at random in the rectangle, and then the experimenter is telling you, it's telling you in the table what the experimenter saw was the result. So how many times was a point below this function? Okay, and so then this is equal to 15 over 17, which is 0.8824. All right, and so then that means that now that this is an approximation of that definite integral. Okay, and this is called the Monte Carlo estimate. Okay, good. Okay, let's keep going. So next is 6.3, which is on mathematical expectation of a function of a random variable. Okay, so we've been finding the expected value of random variables Now we want to talk about the expected value of a function of a random variable. So this is definition 6.3. And so let capital X be a random variable defined on a sample space, capital S. Let little g be a real valued function defined for values x that are possible values of capital X, or negative infinity is less than x less than infinity. Okay. Another way of describing possible values of x, a random variable g of x is defined on capital S as follows. For each little s in capital S, g of capital X of S is equal to g bracket x, capital X of little s. Okay. So what does this mean? So what it's saying is that, so a random variable is like a function where you input a result of the experiment and it outputs a value, a number, right? So you have an experiment. For each thing, for each possible outcome of the experiment, you plug into this function and it outputs a number, right? So your x, your original x was a random variable. It's a function where you plug in results of your experiment. For each result, it spits out a number, okay? We want to say that g of capital X, where g is a real value function, defined for values of x that are possible values of capital X, we want to say g of capital X is also a random variable. So on the whiteboard, I'm going to illustrate how that is. Okay, so originally we have a function, we have a random variable x, right? Which is a function where if you input possible outcomes of the experiment, little s, it outputs capital X of s, right? This is our random variable, capital X. It's a function, okay? A random variable is a function. Now we want to talk about how g of x is a random variable. Okay, and so the definition I gave was that g of capital X of s is equal to g of bracket capital X of s. Okay, so once you're familiar enough with functions, you can figure this out by looking at the equation. So so x is already a function, right? X is a random variable. We're given that x is a random variable. So x is a function where the input is s and the output is x of s, right? The x of s is the bracket in there. G is now performed on x of s. And so now we're going to take that x of s we got out of the random variable x, and we're going to input that into another function. And that function is given to us by g. We're given g also. We're given x and we're given g. And so then when we put in x of s into g, the output is g of x of s. Okay? And so our random variable, g of x of s, we have g of x of s, right? But the random variable is the g of x part, right? G of x is a random variable. So as a random variable, what it is it is a function. G of capital X is a function where if you input s into it, see the parentheses s, if you input s into it, the output is g bracket x of s. So what g of x is a random variable. It's a function, which is a composition of those two functions in the picture. Okay, so it's a composition of first the random variable x and then the function g. So you're post-composing the random variable x with g to get the function or random variable g of x. So this is a machine diagram representation of the functions in this equation. Okay, so this machine diagram is illustrating how we get the function g of x from the function x and the function g. You compose them. Okay, so this part here, this x of s, is illustrated by this. Okay, and then the G part, what comes afterwards, the G part is then illustrated by that. Okay, so we're taking G of, the thing in brackets is the pink part, and then the green part is then taking the result of that purple bracket, that's X of S, and inputting into G. And the result is now G bracket X of S. On the left-hand side, G of X is a function whose input is S and whose output is G bracket X of S. Okay, so you have to look at that for a while, and hopefully that, I think that illustrates it pretty well. So if you look at that long enough, I think that can make sense. So hopefully it does. So this is example 6.14. Let capital S be the experiment of rolling 2 dice, and let S equal to the set of all I comma j, such that I is equal to, I is from 1 to 6 and j is from 1 to 6. So I'm going to write that a little bit shorter. Both I and j are between 1 and 6. So let that be the sample space for our experiment capital S. Let capital X be the sum of values of 2 dice, so that X of I comma j is equal to I plus j. And this is for I comma j in capital S. So what am I saying? So let capital S be the experiment of rolling 2 dice. And so we can represent the sample space of that experiment by the set of all ordered pairs I comma j, where the first component I ranges from 1 to 6, and the second component j ranges from 1 to 6. Okay, so the first component is the result of the first roll. The second component is the result of the second roll. So the ordered pair in total tells you the results of both rolls. And the set of all those ordered pairs is the set of all possible 2 rolls of those dice. So we have our sample space S. And let X be the sum of the values of the 2 dice. Well, if X is the sum of the values of 2 dice, then what you're inputting into X is a point of your sample space, right? Is a simple outcome of your experiment. And your simple outcome is represented by this ordered pair I comma j, where I is the first roll and j is the second roll. And so if X is going to capture the idea of the sum of the 2 dice, then if you're inputting I comma j, the output should be I plus j, adding the number you get from the first roll to the number you get in the second. So I plus j. Okay, and this is defined for all I comma j in the sample space S, which is the set of ordered pairs, right? Okay, so X of I comma j is a function, a random variable where the input is an ordered pair I comma j, and the output is the sum I plus j. Okay, let G be the function G of X, which is equal to X squared. And this is for negative infinity less than X less than infinity. What is G of X? Okay, so the question is, what is G of X? So by saying what is G of X, what we're saying is what is the function G of X? Okay, because random variable is a function. So G of X as a function has as an input I comma j. You're inputting G of X is a random variable, and so just like any random variable, each input is a simple outcome of your experiment, which is an ordered pair, in this case I comma j. And so G of X of I comma j is equal to G bracket X of I comma j. Okay, you're applying X first and then G to your simple outcome. Just like this picture, G of X is first your random variable X, then your function G. Okay, by the big picture here, right? G of X is first applying the random variable X, which is a function, and then post-composing it, then afterwards G. And so when in math, when you write a composition of functions, you write it from right to left. So then you write it, well, the thing on the left is the last function, the composition, and then the thing on the right is the first one, right? So you're going from right to left in order of functions that you apply in your composition. Okay, so first X, then G is then G of X of I comma j. Okay, well, what is x of I comma j? X of I comma j is I plus j. And so it's g of x of I comma j, which we said is I plus j. Okay, so it's g of I plus j. Well, what is the function g? It's just when you have an input for g, the output is squared. G of x equals x squared. So it just takes your input and squares it. And so g of I plus j is I plus j squared. Okay, and this is for any I comma j in capital S. Okay, so g of x is the random variable that represents the square of the sum of the values of two dice. Okay, so it's a random variable where for any two rows, you take their sum and then you square it. That's g of capital X. It's a function on the sample space that assigns a number to each simple outcome of your experiment. Okay, for the function g of x above, we may write x squared instead. Okay, so instead of writing g of x where g of capital X where g of x is x squared, you can instead write x squared. And what that says is it's saying you're squaring the number. You have your random variable x, and then you're squaring the result. Okay. And so similarly with that notation in mind, similarly, if g of x is equal to a naught plus a1 x plus a2 x squared plus a3 x cubed plus dot 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 plus a sub n x to the n. So if g of x is that polynomial function, then g of capital X, where capital X is your random variable, is written as a naught plus a1 capital X plus a2 capital X squared plus a3 capital X cubed plus dot 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 plus a sub n capital X the n. So you want to speed things up. You don't want to write g of x equals this entire thing and then all that. So this is a faster way to represent g of capital X. You just write it like that. You just bypass this g of x and you go straight to the idea that it represents. Okay. Okay, and so now we have a function of a random variable, which is itself a random variable. And so in the next section, we want the mathematical expectation, the expected value of a function of a random variable. Okay? So we have the expected value of a random variable directly, but now we have a function of a random variable. We want to know that the expected value of that. So this is theorem 6.2. Let capital X be a random variable with probability function f of x. Let little g be a real valued function defined for values little x that are possible values of capital X, or from x finite values of little x. The mathematical expectation of the random variable g of capital X is the quantity e of g of x, which is equal to, so there's two cases. One case is when you have a discrete random variable, and the other case is when you have a continuous variable. So this is just like an expected value before, because we had a separate equation for each before. So if x is discrete, then the expected value is the sum over x of g of x times f of x. This is if x is discrete. If capital X is a discrete random variable. I wrote it out just to help you remember that. Okay, so then if x is a continuous random variable, then our expected value is the value of an integral. It's the integral from negative infinity to infinity of g of x times f of x dx. And this is if capital X is a continuous random variable. Okay, and so this is the expected value of the real value of the random variable g of capital X. Okay. For the discrete random variable case, normally it would be the sum over x of x times f of x. But since it's now g of x, instead of the values being values of x, they're values of g of x. And so instead of having x's here, you just have g of x's there, right? So that's the only difference, right? You're still multiplying by the probabilities f of x because your value g of x corresponds with the value. The probability of g of x is the same as the probability of x, right? It's f of x. You're just summing over all possible values of g of x, which is g of x as x ranges all over all possible values of capital X. So you have those g of x's, and you're multiplying each of them by corresponding by the probabilities f of x. And the sum of the products is the expected value. And for the integral, you're just integrating. So you have g of x times f of x, and you're integrating over all possible values of little x, which is from negative infinity to infinity. Okay, so this is provided the series converges absolutely in the x's discrete case, and that the integral absolutely, and that the integral is defined in the x is continuous case. That x is a continuous random variable, and the first one, x is a discrete random variable. Okay, so in order to say the expected value of g of x is equal to the sum, it has to be true that the series converges absolutely. Okay, so if you're taking the sum over infinitely many values of x, you have an infinite sum. Some infinite sums converge to a finite number, and some infinite sums do not converge to a finite number. They can tend to infinity as one possible thing, right? But as long as your sum converges to a finite number, you could then talk about the expected value of g of x being that sum. Okay, and if x is a discrete random, if x is a continuous random variable, you can talk about the expected value of g of x if this integral is defined. Okay, so if this integral is defined, if it's equal to some finite number, you could then say the expected value is equal to that integral, the value of that integral. Okay. The next example is example 6. Oh, okay. So you know what? I'm going to stop here. Okay. So yeah. Okay. So so we're up to 6.3. So okay. So okay, so you could actually do all of homework 8 now. Okay, I have one more thing to say for 6.3.2, but I've covered enough that you can do the homework. So for homework is all of homework 8. Okay, so the homework is homework 8. All of it. Do next class. Okay, and remember the second exam is on December 9th. Okay. Okay, so the second exam is on December 9th during class. So be here on time, and then the final will be after that. Okay, I have to go. I have another class very soon. Have a good night. So I'll see you soon. Okay, see you next week.